So now let's discuss the case when states may be periodic. Let's define the period for a state in a Markov chain. Let di be the greatest common divisor of all values n, such that the probability of going from state I back to itself in n steps is positive. For a recurrent state I in a Markov chain, we can compute the greatest common divisor of path lengths such that we can go from I back to I. Okay? If this greatest common divisor is bigger than 1, then I is said to be periodic. Okay. If it is 1, then state I is not periodic. Okay. So let's see some examples. Very simple case. States 1 and 2. You go from 1 to 2 with probability 1, 2 to 1 with probability 1. Then if you look at the sample paths in this Markov chain, if you start in 1, you will go 1, 2, 1, 2, 1, 2, 1, 2. If you start in 2, 2, 1, 2, 1, 2, 1, 2, 1. In any case, given that x0 is 1, x2n will be 1, right? For all integer n, and x2n plus 1 will be 0. I'm sorry, will be 2. Will be 2. So clearly there's a periodic situation. And the period of state 1 in this case is what? The period of state 1? Period of state 1, which is d1, is 2. Yes. How about the period of state 2? It's also 2. Is it a coincidence that their periods are the same? Let's see another example. Let's see if the periods of states in a recurrent class can be different. Let's see sort of like a less trivial example. Maybe a state where, maybe let's go one step further, add some more states. What is the period in this case? Now, let's look at this greatest common divisor of all path lengths from 1 back to itself. Well, from 1 back to 1, you can go in 2 steps, right? Because you cross to 2, you come back. Or you cross to 2, and then from there to 3, and then come back in 2 steps. That makes what? 4. 4 is another possible path length. Or 1, 2, 3, 4, 5, 6. 6. Or 1, 2, 3, 4, 5. And then do this again. So 8 is possible. And 10 is possible, etc. So what is the greatest common divisor? Obviously 2. So here the period of state 1 is clearly 2. How about the periods of other states? From 2 back to 2, you can go in 2 steps or 4 steps, or you can, for example, go to 3, go to 4, and do this an arbitrary number of times between 3 and 4, 2n times, and then come back. So any multiple of 2 is possible, but It has to be multiple, all possible path lengths are multiples of 2. Again, the period of 2 is clearly 2. The period of 3 is 2, etc. Again, all states have the same period. But let's maybe sketch another, a little bit more complicated example. 1, 2, 3 are the states that sort of go to each other. But from 3, you can also go to 4. So there is like a cycle here. From 4 to 5, 5 to 6, and to 7, and 8, back to 3. Okay. Now, how about path length in this case for example, consider D1, the greatest common divisor of all path lengths. What are possible path lengths from 1 back to itself? 3 is possible. What else? You can go do this cycle and then come back. 1, 2, 3, 4, 5, 6. Right. 7. And we had 1, 2, so that's 9. And then what else? Any multiple of so basically 1, 2, oh, sorry, going from 1, after I make these 2 transitions, I can make a multiple of these. 1, 2, 3, 4, 5, 6. Any multiple of 6 plus 2 plus 1. So basically 6 and plus 3 clearly for any, I mean, the notation is kind of messed up at this point, but you understand that the greatest common divisor of all lengths, path lengths is 3. I mean, all path lengths here from 1 back to itself are divisible by 3. It's not possible to come back to 1 otherwise. How about 2? One, 2, 3, 1, and then 6 times k, and then 1, 2. Again, the same thing. So basically, this is 3. The period of state 2 is 3. The period of state 3 is also 3. So, but then we cannot go like this by inspection every time. We have to find a statement that is true, like a theorem that we can prove. I claim that in a periodic, well, let's not even state it that way. In a recurrent class, all states have the same period. Why? Well, in order to show this, we need to imagine that we leave a state and then we go to another state. Okay, so we want to, okay, suppose I is one state and J is another state, and we want to show that I and J have the same period. Okay? So take I and J inside this recurrent class. Let me just say this is, so basically this is the proof. Take I and J. From I, clearly, I can take a number of transitions and go to J because they're in the same recurrent class. Suppose the total number of transitions to go from I to j is T1. And then, of course, from j, I need to be able to come back to I. Okay, suppose I come back in T2 steps. Because they are in the same recurrent class, I need to be able to get back to I from j. So what is the total number of transitions from I back to itself when I do this path? The total number of transitions from I back to itself is T1 plus T2. Okay. Right. Now, so T1 plus T2 has to be a multiple of the period of state I, right? So this has to be a multiple of di. Okay. Now, but then, when I'm in J, I can make an arbitrary number of transitions and come back to J, back to J. This is T3. Okay. But then T1 plus T2 plus T3 must be also a multiple of di, because this is T1, T3, T2, this is a path from I back to itself, so the total path length must be a multiple of di. But that tells me that T3 is a multiple of di. If you want m minus k times di, or just say alpha times di. But then for any path, this is true for any path from J back to itself. So this means that any path from J back to itself must be a multiple of di. So this means that the greatest common divisor of those path lengths cannot be less than di. So this means that dj is equal to di. Makes sense? Okay, so then we are relieved. In a Markov chain recurrent class, every state has the same period. And we call that the period of the recurrent class. If the period is 1, the recurrent class is aperiodic. Any questions? No? Okay, now let's see some examples. Let's look at this example with the given transition probability matrix. If we plot, if we draw a Markov chain diagram related to this, let's see what it's going to look like. How about I do this? 1, 2, and 3 are the states. 1, 2, and 3 are the states. What are the transition probabilities? From 1, I go to 2. From 2, I go with equal probability to 1 or 3. From 3, I go to 2. Do you think this is periodic? Yes. So let's see what happens if we look at two-step transition probabilities. Let's compute P2. P squared. 0, 1, 0, 0.5, 0, 0.5, 0, 1, 0, multiplied with itself. 0, 1, 0, 0.5, 0, 0.5, 0, 1, 0. What is this? When you multiply that, you get 0.5, you get 0.5, 0, 1, 0, and 0.5, 0, 0.5. Interesting. Interesting. So how about P3? P3 is 0, 1, 0, 0.5, 0, 0.5, 0, 1, 0 multiplied by P2, 0.5, 0, 0.5, 0, 1, 0, 0.5, 0, 0.5. And the result is 0, 1, 0, 0.5, 0, 0.5, 0, 1, 0. What is happening? Do you see a pattern? What will P4 be? P4 will be the same as P2. Right. This is P. P3, P cubed, is the same as P. And we're going to obtain P4 by multiplying P by this, which is the same thing as multiplying, as obtaining P2, P squared. So P2 will be the same as P4. And so basically, for every even value of the power k, P to the k will be the same as for every, let's just say 2k. Okay, so for every even number of transitions, the k-step transition probability matrix for n-step transition probability matrix for every even value of n looks like this. And for every odd number of transitions, the transition probability matrix looks like this. So basically, the transition probability matrix, when it's multiplied by itself again and again, it goes periodically. Let's just keep this aside for now, and let's switch to this case. Okay. In this case, we have states 1 and 2. From 1, you go back to 1 or to 2 with equal probability. From 2, you go to 1 with probability 0.2, back to 2 with probability 0.8. Do you think this is periodic? Why not, Melis?
It's not symmetric, maybe? Or
that's not really the reason. But yes, please, Semana. Right, there are the self-transition probabilities are going to ruin the periodicity. Let's in fact prove a statement regarding to that. I claim that in a recurrent class, when there is at least one self-transition probability, that's going to be causing the class to be aperiodic. So let me erase all of this. So claim if PII, the self-transition probability, is bigger than 0 for any I in a recurrent class, the recurrent class includes I is aperiodic. What is the proof? Well, the proof is very easy. Remember, di is the greatest common divisor of all path lengths n, such that II n is positive. But then, since self-transitions are allowed, I can obtain, I can obtain any integer, right, as a path length. Obviously, then that is 1. Or think of it this way. I'm going from J back to itself. For example, state J has no self-transition. But of course, state J is in the same recurrent class with I. If it goes to I, at I can make an arbitrary number of self-transitions. So if this path length was K, I can get, original path length was K. I can get K plus 1, K plus 2, K plus 3, etc. A number of consecutive integers. Of course, then the greatest common divisor will have to be 1. All right, so that's a nice thing to know. Then whenever, no matter how complicated the situation is, for example, somebody gave you like this, something like this, and they asked you, is this periodic? You don't have to check anything if you see something like this. Because if there's any self-transition, then periodicity is disallowed. Okay, so aperiodic. All right. By the way, of course, there are other cases that look periodic but are not aperiodic. Let me give you just 2 examples as a side note. I'll erase this part. I'll give you 2 examples. How about this one? 1, 2, 3. Oops. 1, 2, 3. I want to make it look like the other. And then 4, 5, 6. And it goes like, yes. So there's a cycle here and a cycle there. Is this periodic? 1, 2, 3, 1, 2, 3. I can make any multiple of 3 like this. If I go this way, 1, 2, 3, 4. Any multiple of 4. But then add any multiple of 3 to any multiple of 4. Well, the greatest common divisor of 3 and 4 is going to be 1. So this is aperiodic. How about the other? Let's give you another example. Again, 1, 2, 3. We make a cycle. So far, periodic, right? Period is 3. How about I do this? Add the cycle back. Now, any path length can be a multiple of 2, a multiple of 3. So, again, greatest common divisor of 2 and 3 is 1, aperiodic. Okay, good. In fact, it is harder for a Markov chain, for a recurrent class to be periodic than be aperiodic. Okay, so let's look at this case. And we confirmed that it is aperiodic because there's a self-transition. Let's compute the p-squared matrix. 0.5, 0.5, 0.2, 0.8. Multiplied with itself. What do we obtain? I computed it before, and turns out to be around approximately 0.35, 0.65, 0.26, 0.74. Okay? And if you look at the P to the 5, matrix P to the 5, it's 0.2874, 0.74, 7126, 0.2850, 0.7150. Interesting. Does it look like the values are converging to something? It looks like this is decreasing, 0.5 is decreasing. This is increasing to 0.28. This is increasing. I mean, one of the point, so at every time, of course, the sum has to be 1, right? But this number is getting smaller, the other number is getting bigger. And if you look at this row, again, they seem to be converging to the same thing. Right. In fact, you can show that as n goes to infinity, p to the n converges to something like 0.28. In fact, it exactly converges to 2 over 7, 5 over 7. The second row as well, 2 over 7, 5 over 7. And you may ask yourself why. We will answer the why next lecture. Let's continue though with this example. In this example, this is p. Let's consider p squared, two-step transition probabilities. They turn out to be 0.04, 0.48, 0.48, 0.10001. It seems like the second and third column rows, are not changing. Okay. In fact, in this Markov chain, if you take the limit as n goes to infinity of p to the n, you obtain, do you have a guess what will happen to this term? 0. How about these two? 0.5, 0.5. I think you already know why. 0, 1, 0, 0, 0, 1. What does that tell us about the situation? No matter where we start, what is the probability that eventually we end up in state 1? It's given by this column, it's 0. So this is the probability that we end up in state 1 given that we started in 1. The probability that we are in 1 given that we started in 2 a long time ago. The probability that we are in 1 given that we started in 3, right? Because this is the entry P31, right? The probability of being in 3 given that we start in state 1 after a long number of steps. It's 0. So this column gives us the probability of ending up in state 1 after a long number of transitions, depending on where we start. And no matter where we start, the probability is 0. How about this column? What is this column?
Ending up in state 2 from 1 or
2 or 3. Very nice, Melis. So this column gives us the probabilities of ending up in state 2 depending on where we start. If we start in state 2, we are in state 2 with probability 1. If we start in state 3, we will never get to 2. We won't end up in 2. If we start in state 1, that is interesting. The chances are 50% to end up in state 2 or not. We end up in state 2 with probability 50%, right? okay, if we start in state 1, it is equally likely to end up in state 2 or state 3. This is the column that belongs to state 3. Again, depending on where we start, the probability of ending up in state 3 changes. Interesting. Now let's go back to this example. No, let's go to this example. And let's look at the columns. This is the probability of ending up where? In state 1 with respect to where we start. But the entries are the same. So it seems that no matter whether we start in state 1 or state 2, the probability of ending up in state 1 eventually after a long number of transitions is 2.2/7. It doesn't depend on the initial condition, the initial state. Similarly, the probability of ending up in state 2 eventually is 5/7, irrespective of where we start. Interesting. So in this case, the Markov chain sort of forgets its initial starting condition. Here it does not. If you look at sample paths of this process, what do you see? Suppose we start in 1. We can go spend some time in 1 and then go to 2 and then go back to 1, 2, 1, 2, etc. And we may start in state 2. In all of these sample paths, we will have 2s and 1s occurring, and we will show in the next lecture that they will be occurring in these proportions, 2/7, 5/7. The probability that eventually the fraction of time that I see state 1 in a sample path is going to be 2/7. The long-term average fraction of time that the chain spends in state 1 is 2/7. The long-term fraction of time spent in state 2 is 5/7. And that's true for all sample paths. Okay. How about this case? Now, this case, there are 2 different possible future scenarios. Those scenarios where the chain ends in state 2, and those scenarios that we end in state 3. So suppose we start in 1. We can stay in 1 for a little while, and then once we get to 2, we are stuck in 2. If we start, alternatively, we have sample paths that end in 3. If you remember the spider and insect example, we have sample paths that end in state 1 when the insect gets captured, and we have sample paths that end in states 3 and 4, where we have 3s and 4s occurring all the time. So 2 different steady states. Now, this case, this kind of Markov chain, where there is only one future steady state, eventual steady state, is called an ergodic Markov chain. It's an ergodic process. Eventually, if you look at the sample path, the time average fraction of time that you observe a state is equal to the eventual probability of that state. And the probability of state 1 in this case is 2/7. Okay. In this kind of situation, we have a non-ergodic process. Okay. If you look at this sample path, what is the fraction of time that state 2 occurs? 2. I'm sorry, 1. Fractional, so it's, you see 2 all the time. Here, the fraction of time that state 3 occurs is 1. But what about the probabilities of the states of the process ending up in 2 or 3? 0.5. But this 0.5 is not observed in any sample path. This is the non-ergodic case. It turns out, and we will prove it in the next lecture, when we have a single recurrent class, and that is aperiodic, we have an ergodic Markov chain. If we have periodicity, it's a totally different situation. If we have periodicity, you see already that there is no convergence. There is no steady state. Right? If you have periodicity, there is no steady state. Basically, if we have periodicity, the Pij of n's, meaning the probability of going from I to j in n steps as n goes to infinity, does not converge. No convergence. Let me write it over some part that I have space, maybe. So I'll just make up some space here. So if the recurrent class is not periodic, then Pij of n, which is the probability that x n is equal to j given x0 is I, right? Converges as n goes to infinity to something, to some value Pij. Let's call that pi ij. Pi ij. Okay. This is the case that we have, for example, we have here and here. Right? This is the case we have in both of those situations. In fact, the pi ij's are the entries of the P infinity matrix. Now, for example, in example 2, pi 1, 2 is what? The probability of being in state 2 given that I started in 1. 5 over 7. What is the probability of pi 2, 2? Same, 5 over 7. In example 3, pi 1, 2. 0.5. What is pi 2, 2? 1. Interesting. So, in both cases, there is convergence. But in this case, the converged values depend on the value of I, where we start with. Okay, so I'll make one more claim. If there is a single recurrent class, and maybe I shouldn't have worded this first statement as a recurrent class, if the Markov chain is not periodic, then there's convergence. If there's a single recurrent class in the Markov chain, and of course this recurrent class is aperiodic, then the limiting probabilities pi ij do not depend on I. Okay. This is the ergodic case. Okay. So now, I'm sure many of you are now puzzled. How can I obtain these limiting probabilities? Is there a short way of obtaining these probabilities rather than multiplying the matrix P with itself an infinite number of times? And there is, and we will study that in the next lecture. But before we end this lecture, I want to say a few more things about the classification of states and what do we do in various situations. So we've seen a number of Markov chains with let's let me give you one more example. Let's call this example 4. Sort of like a more involved Markov chain. Okay. Now, what kind of a Markov chain is this? What are transient states? How many recurrent classes are there? What are the recurrent classes? 4 is a recurrent class with itself, right? So let's just say recurrent classes are 4 with itself. In fact, when a recurrent class has only one element, we call it an absorbing state. Absorbing state. Remember in the previous lecture, we explored what is the probability of getting absorbed in an absorbing state? We explored, because if there are multiple recurrent classes, it is not guaranteed that we will get absorbed in 4. But we can compute that probability, right? I showed you how you can write a set of equations and then compute that probability. Okay. How about, are there any other recurrent classes?
5, 7, 8.
5, 7, 8 is another recurrent class. 6, 9 is another recurrent class. Right. 2, 3. Mustafa. Are they recurrent? 2, 3. Why not?
Because if you leave 3, for example, and
we will never go back. If we leave 3 and go to 2, yes, we will come back. But if we leave 3 and go to 5 or 6, we will never come back. So there's a way of leaving and not coming back. That means 3 is transient. 2 is also transient. 1 is also transient. So transient states are 1, 2, and 3. So eventually, when you run this Markov chain, the transient states will disappear after a while in the sample path. Even though the sample path may start by showing 1, 2, 3s, eventually they will disappear. Eventually, we will have how many kinds of sample paths? 3 kinds of sample paths. Sample paths that continue with only 4, like the fraction of times fraction of time that we see 4 is 1, right? We see 4 all the time. Or sample paths that contain 5, 7, 8 with certain fraction of time, with certain frequencies, which we don't know how to compute yet. And we will have sample paths that have 6s and 9s. Okay, so this is what kind of a process? Not ergodic. It's not ergodic at all. Okay, so now in this Markov chain, can you answer questions like this? I'll just write you the questions. 1. What is the probability of getting absorbed in state 4? Can you compute this? In fact, we made such a computation in the previous 2 previous lectures, lecture 15. We computed the probability of getting captured by the spider, right? How did we do that? We wrote a set of equations. We said, let AI be the probability, let me just write it mathematically. Let AI be the probability of getting captured in state 4 given that I start in state I. So basically this is the probability that, if you will, limiting probability that xn is 4 given that x0 is I. Okay. And then I can write a set of equations. For example, let's write one for A1. A1 is P11A1 plus P12A2 plus P13A3. Right? Because with probability P11, I go from 1 back to 1, and then again the probability has unchanged. From 1 to 2, I go with probability P12, and then when I'm in 2, what is the probability that I end up in 4? A2. So I can write this equation, and I can write A2 similarly, P23A3 plus P24A4. But what is A4? 1. Okay? I can write A3. A3 is equal to P, what? 2A2 plus P35A5, but A5 is 0. So A5, this is 0, plus P36, A6, again A6 is 0. So these terms are gone. What's next? I can write I don't have to write A4, right? A4 is 1. Okay, basically how many unknowns do I have? A1, A2, A3. A4 is 1. And I have how many equations? 3 equations and 3 unknowns, I can solve this, right? And I can easily compute the probability of getting absorbed in 4 for every state. Nice. Okay, good. Can I compute the expected amount of time of getting absorbed in 4? That's a trick question. I give you this Markov chain and I say I start in 1. What is the expected amount of time until I get absorbed in state 4?
It's not a certain event.
Exactly. This is not a well-defined random variable, the amount of time until I get absorbed, because it is not finite with probability 1. It is not guaranteed to get absorbed in state 4. So I cannot ask that question. But in one of the questions in the previous lecture, lecture 15, we did answer a question about the expected time of getting to a certain state. How did we do that? We looked at a recurrent class. Let's call this example 5. A recurrent class like this, for example. And we asked, here I can ask, let T4 be the expected time or to reach 4. I'm sorry. Wrong. Let me just redefine this. Okay, I'm interested in the expected time to get to state 4. Okay. Let T1 be the expected time to get to 4 given I start in state 1. And in general, let Ti be the expected time to get to 4 given that I start in state I. Now, the expected time to get to 4 given I start in state I is well defined in this chain. Why, Semanur? Because I'm guaranteed to get to 4 eventually. It's a recurrent class. So then I can compute these expectations. How do I compute these expectations? Again, I can write a set of equations. Right? So T1 is equal to P13 T3. Basically, this is it. No, it's not it. What else do I need? Plus 1, plus the transition that I make. Right? 1 transition plus T3 more transitions in expectation multiplied by P13. In this case, P13 is 1 in this example. So how about T2? T2 is 1 plus P22 T2 plus P21 T1. And T3 equals, what? 1 plus T, what is T4? T4 is what? 0 though. T3 is 1. So T3 is 1. From that I can get T1 is 2. From that I can get T2 as, well, T1 is 2, so depends on P21 and P22. I can find T2. Okay, so you see the difference. When I have a recurrent class, the amount of time to reach any state is a random variable. When I have a non-ergodic situation with multiple recurrent classes, then the amount of time to reach a given state is not a random variable. It is not finite with probability 1. Then I can compute probabilities of getting absorbed in those classes. Now, in the next lecture, we will focus on steady state probabilities. Steady state probabilities, and we will try to explore this ergodic case in depth and understand how we can compute the probabilities, eventual steady state probabilities of states systematically. Okay, see you next time.